Let's talk about the change in momentum and the force responsible for that change to occur. First, let's talk about change in momentum. So consider an automobile that is moving down the road and is initially at some initial position. We know the mass and the velocity of the automobile. So the mass is m, the initial velocity is v sub I. And then at some other, or after some time, the automobile is at a different position. Let's call it final position down the road. So the mass doesn't change. The velocity, though, is different. Let's call it the final velocity. So from the definition of momentum, I can calculate the momentum of the automobile at the initial position and the final position. And so the initial momentum, P sub I, is equal to the mass of the automobile times the initial velocity. So let's call this initial momentum. And then at the final position, the momentum is P sub F. So that is the mass of the automobile times the final velocity. So this is the final momentum. So I can calculate the change in momentum by taking the difference between the final value and the initial value. And the change in momentum, delta P, is equal to P final minus P initial. If I wanted to express the change in explicit terms of mass and velocities, then the change in momentum will be equal to the mass times the final velocity minus the mass times the initial velocity. And so this is the change in momentum. So I can calculate the change in momentum for any object that's in motion as long as I know its velocity at any moment of time. So the symbol delta that I've used here for the definition for change, that stands for change in. And this can be used to, or the same principle of calculation of a change can be used for calculating change in all kinds of physical quantities, change in temperature, change in kinetic energy, and so on and so forth, change in volume, so on and so forth. And so the main principle of how you calculate that, again, is to calculate that particular quantity at two different instances of time, and then take the difference between the later value of that quantity minus the earlier value of that quantity. And so we usually call them final and initial. And that difference is the change in that quantity. Now let's see what is the reason for this change in momentum to occur. If you look at my drawing here, the car initially has some velocity, v initial, and then later on has a different velocity, v final. As we saw from the definition of Newton's first law, the only reason for an object to change its velocity is if a non-zero external force was applied to the object. So that means that this car here is under the action of some force. And so that means that the car is accelerating, which means that the velocity will be changing. So there is a relationship between the change in momentum and some external force that acts on this car. The relationship between the external force and the change in momentum is given by the impulse momentum theorem. Before we talk about that theorem, let's define what impulse is. So, one more time, let's look at our example with the moving car. So the car initially is at this initial position. And then some force F is applied to the car. And the car here starts with initial velocity v sub I. So then the car moves down the road under the action of this force and gets to some final position. And now the velocity of the car is different, v sub f. So the force is applied on the car at all times between the initial and the final positions. And then after the car passes this final position, it doesn't matter if the force is applied or not, because we only are interested what happens to the car or to the momentum of the car between those two positions here. Okay, so obviously, as the car is moving, it takes some time to get from the initial to the final position. And so this force was applied on the car during that interval of time. So then it is also important to know what that interval of time was. So let's call that interval of time delta t. And so the product of the applied force and the interval of time delta t is known as the impulse of that force. So F times delta t is the impulse of the force F. The units in which impulse is measured are the units of force, newtons, times the units of time, seconds. So the impulse of a force F is measured in Newton seconds. And so the action of this force F for that amount of time delta t is the impulse of that force. And this impulse leads to a change in momentum for this moving car from its initial to its final value. So then the relationship between the two, the impulse of the force and the change in momentum, is given by the impulse momentum theorem. And the statement of the theorem in a formula form is that the impulse of the force F, so that is F times delta t, is equal to the change in momentum mv final minus mv initial. And so the impulse momentum theorem reads that the impulse of a force F applied to an object of mass m is equal to the change in momentum of that object delta p. From the statement of that theorem, it also becomes clear that the units of impulse, Newton seconds, are equal to the units of change in momentum, which were kilogram meters per second. So let's add that as a side note here. Newton seconds is the same as kilograms meters per second. So what are the applications of the impulse momentum theorem? Well, the first application is that if we know the change in momentum of a moving object and the time interval that it took for that change to take place, the force that was applied to the object can be calculated. And for example, such calculations are performed when safety is concerned in cars. So you may have seen some footage of safety car testing with a crash test dummy in the car collides with a wall, and then they measure the time that it takes for the car to come to a complete stop, and then from knowing the change in momentum of that moving car, the force that's applied to the car can be calculated. And so then adjustments could be made for certain safety features on the car so that the crash test dummy doesn't take as much force as to be harmful for an actual person in the car if the car crashes. So what is the principle of applying those safety precautions as far as the impulse momentum theorem is concerned? Well, suppose that the change in momentum is fixed. Let's say a car is moving with some initial velocity of 30 kilometers per hour, and then it crashes and comes to a dead stop, so the final velocity is 0. So the change in momentum is fixed. Okay, then that means that certain impulse was applied to the car for this change of momentum to happen. But the impulse is the product of two terms, force and time interval. So we know the value of the impulse, but we notice here that if I vary those two terms accordingly, I can minimize the amount of force required for the change in momentum while increasing the amount of time for which this force was applied. And so for safety in cars, for example, that is exactly what is done. By adding airbags, crumple zones in the cars, and other features, the interaction time, the time that is required for the car to come to a complete stop, is increased. And then that means that since the change in momentum is constant, the force that the car experiences is decreased, which then in turn means that the person that's inside the car will experience less amount of force when the collision occurs, which increases the chances of less, smaller injuries or survival in general for that person in the car. Here are some other examples that also illustrate the concept of reducing the amount of force while increasing the interaction time for the same change in momentum. For example, you may have seen or done an experiment where an egg is tossed against the wall versus an egg tossed against bed sheets. And so you know that if you toss an egg against the wall, the egg is going to break because the momentum of the egg changes almost instantaneously because the interaction time with the wall is very short. Therefore, the force that acts on the eggshell is pretty large, and thus the eggshell breaks. Now, if you throw the egg at a bed sheet, what happens is you observe the same change in momentum. However, the interaction time with the bed sheet is much larger compared to the wall, which then reduces the force that the eggshell experiences, and then this force is not enough to break the eggshell. Another example would be dropping a glass on a bare floor versus thick carpet. You know from intuition that dropping a glass, and from experience of course, that dropping a glass on a bare floor will result in the glass breaking. However, if you drop the glass on a thick carpet, chances are that the glass will not break. And again, what happens is for the same change in momentum in both situations, the interaction time is different. For the bare floor, this interaction time is small, and for the thick carpet, that interaction time is large. So, for the bare floor, the force that acts on the glass is much larger compared to the thick carpet, and therefore the glass breaks when you drop it on the bare floor, and it doesn't when you drop it on the thick carpet. Let's illustrate the concept or the impulse momentum theorem with an actual example. So, here is my example. Again, I'm going to use a moving car, which is going down the road. At the initial position, the car has initial velocity of 10 meters per second. And let's say that the mass of the car is 1,000 kilograms. And so the car moves down the road, reaches this final position. And the velocity of the car now is 20 meters per second. The mass remains the same, 1,000 kilograms. Let's assume that the car did not travel long enough distance to burn enough fuel so that the mass changes. And also, let's say that the time interval between the initial and final position is 5 seconds. So then the question is, how much force was applied on the car for this change in velocity to occur? And so in order to solve this problem or answer this question, we must apply the impulse momentum theorem. The impulse momentum theorem states that the force times the interval of time for which the force was applied, so that is the impulse of the force, must be equal to the change in momentum. Okay, so since I'm looking for the force, from here I'm going to rearrange the terms in this formula and solve for the force. So the force will be equal to mv final minus mv initial divided by delta t. Now I know all the quantities on the right-hand side. I know the mass, I know the final initial velocities, and I know the time. The units for mass and velocity are the units that I want for calculating the values of the momentum at the two positions. So there is no need to do any conversions. So let's then substitute and calculate. So the force is equal to 1,000 kilograms times 20 meters per second minus 1,000 kilograms times 10 meters per second divided by 5 seconds. So this is equal to 20,000 kilograms meters per second minus 10,000 kilograms meters per second divided by 5 seconds. This is equal to 10,000 kilograms meters per second divided by 5 seconds, or this is 2,000 kilograms meters per second squared, or 2,000 newtons. And so this is the force responsible for this change in velocity between the initial and final positions of this car moving down the road.